Welcome back. In this chapter, we are going to talk about the timers or counters that are available in the ATmega. The beauty of those timers are that they run automatically in the background and in parallel to the CPU that is then free to execute your program code. The timers are quite flexible and the functionality ranges from counting, measuring time, informing your program that a specific time has passed, to the generation of waveforms and signals. What are we going to cover in this lecture? First, we have to define three terms that are used throughout this lecture and that describe important concepts. Then we dive into how the timers operate, their modes and purposes, and what the differences among the three timers are that we have in the ATmega 328P. You might have more timers if you have an Arduino Mega, which has 6 of them, or less if you have an ATtiny, which has only 2. However, the concepts introduced here are the same. Please note, timers are very strong and used often, especially in conjunction with interrupts. An interrupt is a concept that we are going to handle in the next chapter, and we will talk about timers there again. This chapter covers the foundation of timers and will get you ready to use them. By the way, the term timers and counters is interchangeable and I will be using both of them. Let's see what a timer or counter does. Well, it is quite obvious. It counts. There is a register called TCNT followed by an N, which represents the number of the counter under consideration. So in ATmega 328P, we have TCNT0 to TCNT2. So each timer has its own counting register. Here we see a clock signal, also called clock Tn. Every timer can have its own clock signal, different from the system clock or even independent of any clock. The clock is a rectangular signal having essentially two states, that is high, for instance here, and low, for instance here. At the transition from low to high of the clock signal, which is also called the positive edge, the counter register increments. At the negative edge, that is here, nothing happens. That is a simple yet powerful functionality, as we will see in a minute or two. But before that, we have to define a few terms. First, max. Max always represents the maximum value a TCNT register can have. It is a constant. For instance, for 8-bit counters, the maximum will always be FF in hexadecimal format. For 16-bit counters, it is FF in hexadecimal or 65,535 in decimal format. What happens if a TCNT reaches max? Well, it's quite simple. It does not care and keeps incrementing. However, at max plus 1, there are no bits available anymore to represent that number. So the counter overflows and restarts from 0. This example shows how it looks like for two counters, counter 0 and counter 2. It is similar for counter 1, which is a 16-bit counter. After reaching 65,535, the next value will be 0. The next term is bottom. That term is also quite easy. It is the lowest value a counter register can have, and that is all bits in the TCNT register are cleared. Therefore, bottom is 0 and it is always 0. And we have top. Top is the value that TCNT counts to before flowing over and restarting at the bottom. The difference to max is that top is configurable. It could be that top is equal to max, but it does not have to be. Top can be any value between max and bottom, including those values. Here in this example, top is set to 100 and although TCNT could count to higher values, after reaching top, it restarts from 0. Okay, that's all about the definitions. How do the timers actually work? This is a block diagram of a counter. There might be some differences based on the functionality offered by the counters, which I will point out separately. However, this diagram shows the common functionality that all counters have. On top, we have some control logic and clock generation. Then we have the TCNT register, which does the counting. We also have OCRnA and OCRnB, which stands for on compare register, so they are used for some comparison. And at the bottom of the diagram we have TCRnA and TCRnB, which are the configuration registers for this particular timer. On the right we have some pins called OCRnA and OCRnB, so something that the timer generates can be exported to the outside world. And on top we have TN, which seems to be an input pin. Important to note that all registers such as TCNT and OCRnA and the configuration registers are connected to the data bus and therefore accessible in the same way like the ports and the data direction registers. Hence, if in a source code it is mentioned that TCNT0 is set to 1, 2, 3, then this register will be set with immediate effect as the CPU has priority over the increment command writing to the TCNT. Also, the configuration registers are accessible and updated immediately. However, that is not true for the OCRs. While you can write to the registers at any point in time, the changes to those registers will become effective after some delay, which depends on the mode the counter is currently in. I will point out when these updates happen in each of the modes discussed in a bit. OCR is therefore also called a double buffer, since your new value will be stored temporarily somewhere else before being copied to the actual register OCRnA or OCRnB. Okay, let's start with the configurations that we can set in these two registers. The meaning of the other registers will then become clear along the way. There are 3 different modes: normal mode, clear timer on compare match, and pulse width modulation, abbreviated as PWM. Further, there are 3 different flavors for the PWM mode, that is fast PWM, phase correct PWM, and phase and frequency correct PWM. We can also configure the clock frequency and its source, interrupts, and what kind of waveform to be generated. This lecture is about timers, hence we will postpone the interrupts to the next chapter. Only this much now. Timers become incredibly powerful in conjunction with interrupts. However, first we have to cover some basics. In the following sessions, we will go through each of the modes, how to configure them in the configuration registers shown below, and how to choose the clock source and frequency. We will start with the easiest. We have a look at the clock sources for the timer. These 3 bits in the TCRnB register, marked in red here, configure the clock, which essentially affects this region in the block diagram. Let's zoom in a little bit to see what we have here. On the right, there is a pin called TN. Again, N stands for the number of the timer. The pin overview reveals that PD4 and PD5 are connected to T0 for timer 0 and T1 for timer 1 respectively. There is no T2 for the third timer, so it must be something special, and I will show you in a bit. Back to the clock generator for our timer. Internally, the pin Tn is connected to an edge detector. An edge detector is a hardware unit which, as the name suggests, detects edges in a signal. So if the edge detector is configured to detect positive edges, it will generate a signal whenever that transition is encountered, as shown in the diagram below. For instance, here and here. It can also detect negative edges, and they do not have to be in regular intervals at all. Since you already know that the timer increments at the positive edge of the clock, the timer literally counts the number of spikes by now. Maybe you would like to count button presses or the number of clock pulses from a connected periphery. Based on the configuration, either the signal from the edge detector will generate the clock for the timer, or alternatively another source which comes from the prescaler. What is a prescaler? A prescaler is a hardware unit that can decrease the clock frequency. The input to the counter prescaler is the I/O clock, which runs at the same frequency as the system clock. As shown earlier, that is 16 MHz. The prescaler can be configured. It can be set to block the incoming clock entirely, essentially turning off the counter. Or it can leave the clock signal untouched, and hence the frequency of clock Tn is the same as clock I/O. In that case, the prescaler is set to 1, indicated by the denominator here. A prescaler of 2 would halve the original clock frequency, and the prescaler of 4 would quarter it. Since it slows down the frequency, and since the counter register increments with every positive edge of the clock, such as this one and this one, a higher prescaler makes the TCNT count slower. There are several prescalers available. The largest one is 1024, the lowest one is no clock source, so the counter does not count at all and is stopped. That switched off state is the default after a reset. Therefore, configuring the bits CSN2 to CSN0 is mandatory to use the counter in the first place. Please note, not all prescalers are available for all timers. The same is valid for the edge detector. Not every timer has one. Remember, timer 2 does not even have the pin T2, so no edge detection here, but it has more prescaler settings. What about the specialty of timer 2? Well, timer 2 is connected to 2 pins called TOC1 and TOC2 and an oscillator. Alternatively, the timer can also be clocked using the clock I/O, depending on the setting of the signal AS2. Both signals are fed into the prescaler, which then generates a clock signal called clock T2S. That is quite different compared to the timers that we had so far. Where are TOC1 and 2? They are connected to PB6 and PB7, shown here. Compared to the previous prescalers, this timer has 2 more dividers, 32 and 128, which do not exist in timer 0 and 1. Timer 2 does not have an edge detector nor a Tn input pin, hence those settings are missing here. But what is the purpose of the special timer 2? TOSC with the oscillator suggests it already. It offers the option to run timer 2 entirely independent of the system clock. Imagine that your ATmega runs at the clock frequency of, let's say, 8 MHz. This frequency can be slowed down by the Prescaler to some extent. However, what if you need an entire different frequency, such as 122 kHz? In that case, you can connect a crystal to TOSC1 and 2 with the desired frequency of 122 kHz. Since a crystal needs 2 connections, 2 pins are required. Consider a specific scenario. The system clock usually runs at 128 kHz, 1 or 8 MHz if TOSC1 and 2 are used. Connecting a crystal that swings at a frequency of 32.768 kHz means that timer 2 will increment 32,768 times per second. That means that this timer can be used as a real-time clock. Since timer 2 has an 8-bit counter, the TCNT2 register needs to overflow 32,768 divided by 256, which equals 128 times, to count for 1 second. That can be easily checked in software. Further, with this frequency, the resolution is approximately 30 microseconds between 2 consecutive increments. Alternatively, if the Prescaler is set to 1024, the number of overflows per second reduces to 0. At this Prescaler, the register is incremented 32 times per second, and since 32 is less than 255, no overflow occurs. However, then the resolution also decreases to around 31 milliseconds between 2 ticks. If the Prescaler is set to 128, a setting that is not available with the other timers, something interesting happens. TCNT2 overflows exactly once every second, so we can stop the CPU every second to do something else. Between 2 increments, around 4 milliseconds pass, so we can distinguish at most 4 milliseconds while waiting for the next increment. That's nice, isn't it? Now we have an accurate notion of time available in our program, and you know how many seconds have passed since the ATmega was powered on. A crystal with a frequency of 32,768 Hz is very inexpensive, and it costs around 50 US cents. In addition, its space and power consumption is very low compared to an external real-time clock. Therefore, it is a very easy way to measure time. That's all regarding the clock signal generation for the timer. Each timer in the ATmega can be configured in 4 or 5 different modes, changing its behavior. In the next few sessions, I will introduce each of those modes, starting with the simplest one, the normal mode. If the waveform generator mode bits, or WGM in short, are all cleared in TCCRnA and TCCRnB, that is, they are set to 0, and the CS bits are configured according to the desired source or Prescaler, the timer runs in the normal mode. There is nothing special in that mode. The x-axis of this diagram represents the time, while the values of TCNT continuously increasing till the top, which is the same as max, are on the y-axis. After reaching max, the register overflows and restarts from the bottom, that is 0. So over time, we get this sawtooth waveform. Together with the Prescaler, we can determine how steep the curve will be. If the Prescaler is 1, the curve is steepest. The higher the Prescaler, the flatter will be the curve over time. But What if we do not want to run to the max value? What if we want to increment the counter till a defined value that is less than max? In the normal mode, we do not have a choice but to implement this functionality in software. So we continuously check the value of, for instance, TCNT0, and once it crosses the desired threshold, we reset the TCNT register and do what we plan to do. That means the sawtooth waveform becomes like this. Depending on the threshold, the teeth are more or less sharp. However, this is a software implementation and hence requires CPU resources. While we wait for the TCNT to cross the threshold, we cannot do anything else. Further, it is unlikely that the while loop exits when TCNT is exactly 200. It might be larger than 200, since CPU resources are required to read TCNT, to evaluate its value, and to jump to the beginning of the while loop as long as the condition is true. The advantage of timers ought to be that they run in parallel to the program. However, for this program, that is only true while the do something part is executed in parallel with the incrementing of the TCNT0 register. Therefore, it would be nice to have hardware support for a lower top value. And it turns out that we do, as it will be shown in the next session. The mode in which the timer runs normally, however with a top value that is lower than max, is called clear timer on compare match mode, or CTC mode in short. To accomplish CTC, we need to have a look at the middle section of the block diagram. This is a closer look at the cleaned middle section. We have the TCNT here, which contains the register that keeps incrementing. And we have another register called OCRnA, which stands for Output Compare Register. In the middle of the two registers is a comparator. If both values in these two registers are the same, this signal goes up. It is used to reset TCNT, and therefore the top becomes a value that can be less than max. In addition, the same equality signal goes into the waveform generator, which in turn is connected to a pin called OCRnA. What does the waveform generator do with that signal? It can be used to generate a waveform on this pin. Whenever the top value is reached, the pin toggles. So if top is equal to max, the period, that is the entire cycle of the signal from low to high and before it drops again to low, or vice versa, is maximized. A lowering of the top value shortens the period, as you can see here. Depending on what the ATmega is used for, some peripherals need an external clock input. The CTC perfectly allows to generate such a signal with an equal time for the low and high section of each period. If a faster clock is required, a lower top is used, while a higher top value results in a slower clock and therefore longer period. Looking at the block diagram, it becomes clear that despite the timer has two compare units, namely this one and this one, only OCRnA is able to reset the counter when top is reached. As you can see here, the comparator is also connected to the control logic which is able to clear TCNT. However, both compare units have dedicated pins. Where are those OC pins? All timer-related pins are marked in magenta in this figure. So we have two waveform generators for timer 0 connected to OC0A and OC0B. We have also two pins for timer 1 and two pins for timer 2, here and here. To activate the CTC mode, the WGM bits need to be set to 010 in binary format. That is, WGMN2 and WGMN0 are set to 0. These are these two bits. And WGMN1 is set to 1. In addition, OCRnA needs to be configured so that the timer knows which value to count to at maximum. Do not forget that the clock source and Prescaler need to be selected as well before TCNT even starts running. To toggle the pins, COM-NA or COM-NB need to be set to 1. In addition, and that is important, the pin needs to be configured as an output, otherwise no signal is emitted. That brings us to a question. Imagine that a peripheral device is connected to the OC pin. This device expects a specific frequency as input clock. How to calculate the top value for such a frequency? Let's do some math about the frequency of the OC pin. Given is an I/O clock of 1 MHz, a prescaler of 1, and an 8-bit counter TCNT. What is the resolution of the timer? That is, checking the value of TCNT and waiting till TCNT is incremented. Once that happens, we know that a specific amount of time has passed. Hence, the question is, with the given parameters, what is the difference in time that we can measure at minimum? That value is also called the resolution. Please pause the lecture here to give you time to think about this problem. After the counter in the right corner reaches 0, I will present the solution. Did you get it? What is the resolution of the timer? So we have the resolution of the timer, which is equal to 1 divided by the I/O clock divided by the prescaler, which equals 1 divided by 1 into 10 to the power of 6 Hertz divided by 1. That is the prescaler. That equals 1 into 10 to the power of minus 6 seconds, which is 1 microsecond. The next question is, what is the highest frequency that the pin OC can emit with the given parameters? For the fastest frequency, we set OCR to 0 so that TCNT reaches the top value every single time. Remember, when the TCNT drops from top to bottom, the OC pin toggles as shown here. What is its frequency? To compute the frequency, we have to use the entire period of this signal. Let's call this time TOC. To maximize the frequency, the time TOC needs to be minimized. That is, the time from here to here is shortest. As you can see, the timer in this period increments twice. Hence, the minimum time is equal to 2 into the resolution of the timer that we calculated on the previous page, and that is 2 into 1 microsecond, which is obviously 2 microseconds. Therefore, the maximum frequency of this pin, that is FOC, is equal to 1 divided by the minimum time, that is 2 microseconds, which equals 0.5 into 10 to the power of 6 Hertz, which is 500 kilohertz. That is half of clock I/O. Since there is no prescaler lower than 1 except turning off the counter entirely, the maximum frequency of the pin is always half of the system clock. Another question: what is the lowest frequency that we can do on this pin with the given parameters? For that, we have to set OCR to the highest possible value. What is the frequency now? Okay, this time we want to maximize the entire period of this signal, which goes far beyond the screen here. Again, this is TOC. Therefore, we have to maximize this time, which is the resolution, into 2, because we have to toggle twice to get one period from the low to the high signal, into the number of increments that TCNT needs to overflow, and in this case it is 255, which is the top value, plus 1. Hence, till here we increment 255 times, and to overflow we have to increment one more time. Hence, 256 increments are required till the pin toggles. This results in 512 microseconds. Therefore, the slowest frequency of this pin is 1 by this maximum time, which is 1053 Hertz, or almost 2 kilohertz. Obviously, with higher prescalers or larger counters, even lower frequencies are possible. So the relationship between the frequency of clock I/O and the frequency of the pin can be expressed as the fraction of the I/O clock divided by 2 into the prescaler into the value of OCRnX plus 1. Again, the reason for this plus 1 is as follows. Imagine you set OCR to 100. How many times need TCNT need to be clocked starting from 0 to overflow to 0 again? First, it has to count to 100, which takes 100 clock cycles. Then TCNT needs to be cycled one more time to overflow. Hence, for every round, 101 clock cycles are required. Please keep that in mind when accurate timings are required to count to one less in OCR. Later, more about this in the exercises. That's all what I have about the CTC mode. There are more scenarios discussed in the next chapter about interrupts, in which the CTC becomes one of the most powerful tools available to execute code in fixed time intervals. This session will be about the fast pulse width modulation, the next mode the timer supports. But before going there, let's have a look at the following blinking LED code once again. As you can see, every second we toggle the LED. That means the LED is on for a second and off for another one. Ergo, the period is 2 seconds. If I want to reduce the time and make it blink faster, I reduce the parameter in delay ms. Simple, right? So I can make the blinking of the LED arbitrarily faster. What happens if I make it extremely fast with very short periods?
Okay, a little experiment. Here we have an Arduino and two LEDs. One of them is constant on, the other one is blinking. The constant on LED is connected to 5 volt, then to this resistor to the ground. The blinking LED is currently connected to pin number 10, which is a PWM pin. Same resistor and then the ground. The little blue box here is a trimmer. It is a resistor whose resistance value I can configure based on a setting of this screw. This resistor is then connected to the ADC and pin number A0. The ADC we are going to have in the chapter later in the course. I'm going to upload the circuit diagram, which then can be found in the resource folder attached to this lecture. In this ATmega, there's a program running, reading the analog value coming from this resistor and configuring the PWM in the period time. Changing the value of this resistor will shorten the period time, making this LED blink faster. So let's do that and see what happens. So it's getting faster and faster and faster, and in one point in time it's so fast that there's no difference anymore between the on LED and the off LED. It looks like as if both of them are on at the same time. I'm not sure if it's visible to the camera, but this LED looks a little bit darker in brightness than the LED that is constant on. For the human eye, I cannot distinguish these on and off periods any longer.
To make the LED a tad brighter, I could increase the on time a little bit and reduce the off time by the same amount, keeping the period constant. The ratio between the on time and the entire period length is called duty cycle. It is usually given in percent. So, in the middle timing diagram, the on and off timings are equal, so the duty cycle is 50%. In the lower diagram, the ratio is 3:1 between the on and off time, so the duty cycle is 75%. Constant on would be a duty cycle of 100%. Constant off is 0%. As you can see, no matter the duty cycle, the period always remains the same.
Another experiment. In this experiment, the circuit is exactly the same compared to the experiment that we had earlier. What I changed is the program running on this ATmega. Instead of configuring the period using the trimmer, I now can configure the duty cycle. And if I change the duty cycle to a longer off period, you can see that the brightness of the LED reduces. So you can turn it on and turn it off, or leave it somewhere in the middle.
In the CTC mode, the period changes and the duty cycle remains constant. As you can see in this period, the duty cycle is 50% as well as in this one, albeit the period is shorter. However, for the blinking LED scenario, we need something that can change the duty cycle but keeps the period constant. That is where pulse width modulation, or PWM in short, comes into play. As you can see, in this mode the counter counts to top, or max in this case. Again, top can be lower than max, and we are going to talk about that in a second. Instead of the OC pin toggling, there are two different settings for the COM and X bits in the timer configuration register now. If the bits are set to 2, then whenever TCNT overflows, the OC pin is set to high, for instance in this case or in this case. When TCNT equals the value stored in OCR, indicated by these green bars, the OC pin signal is set to low again, shown here or here. If COM and X is set to 3, then the OC signal is inverted. That is, when TCNT overflows, the OC signal is set to low, like here or here. And when TCNT equals the value stored in OCR, the OC signal is set to high. As you can see, the period remains the same by now, but depending on the value of OCR, I can determine precisely the on and off time ratio in every period. There are two special cases. If OCR equals top, such as in this scenario or in this scenario, then the OC pin is either constant high, shown here, or constant low, shown here, depending on the COM and X setting. If OCR is set to 0, then there is a tiny little spike on the OC pin every time the timer overflows. If WGM is set to 3, then TCNTN counts to top. However, if the WGM bits are set to 7, that is, all entries are set to 1, then a top value can be configured manually. That combines the CTC mode that we had earlier with PWM and allows not only to configure the duty cycle, but also the period. If the PWM is configured in that way, OCRnB needs to be used to create a signal with a duty cycle, as OCRnA is already used to reset the counter once it reaches the top value. If the standard period is fine, that is, TCNT counts to max, both OCRnA and OCRnB can be used to configure the duty cycle independently with the same period. Here we see a top configuration in action. OCRA contains the new top value marked in blue. Here and here top is set to max. However, after that, the top is lowered to a value less than max. By doing so, and as you can see, the period becomes shorter, which means that the frequency increases. So we combined CTC configuring the period length and PWM determining the duty cycle. That's all what I have about the fast PWM. In the following exercises, you have to use PWM to make the LED blink without using the delay ms function. Have fun, and I will see you in a bit in the next session about another PWM mode, the phase correct PWM. The next mode on the agenda is the phase correct PWM. So let's talk about that. In this mode, the timer register does not overflow. After reaching top, it decrements till the bottom value, after which it restarts from the beginning again, increasing the TCNT n value. If the timer increments and passes through OCRnX, the OC pin is set to 0. On the way down, the OC pin is set to 1 once TCNTN equals OCRnX. Like in a fast PWM mode introduced in the previous session, the waveform is inverted if all COM and X bits are set. You might ask, okay, so I have fast PWM and phase correct PWM. I can set the timer in the fast PWM mode to generate a waveform that is identical. So what is the purpose of having a phase correct PWM mode? That is a valid question, and it is absolutely true. You can generate the same waveform if you run the timer in fast PWM mode. However, the difference is how the waveform changes if OCR is modified. This slide compares the two different modes. On top is the phase correct PWM. The lower waveform has been generated by fast PWM. As you can see, its waveform always starts going high at the beginning of the period. In the phase correct PWM mode, the high signal is centered around the beginning of the period. That means one half of the high signal belongs to the previous period and one half of the high signal to the next one. So if OCRnX is changed, that width is changed at the beginning of the period. So when should you use what mode? Phase correct PWM is designed for motor applications in which you have to control the revolutions. Another difference is that when OCRnX is set to the bottom, the pin does not generate anything but a constant high or low signal depending on the COM and X bit configuration. Especially in the beginning, motors draw a high current to start spinning. Imagine that you tickle the motor always with a short pulse in regular intervals. That pulse is too short to start the motor, but it consumes power nevertheless. The pulse is created when the timer runs in fast PWM and OCR is set to 0, as shown by the red little glitch here. In contrast, due to the higher frequency possible in fast PWM, it is designed for power regulations or digital to analog conversion, abbreviated as DAC applications, in which intermediate voltages need to be generated. Let's have a look at why fast PWM is better for this area of applications. The problem is that the output at the pin is still a nearly rectangular waveform. So either the pin has full voltage or none. Many times PWM is used to create intermediate voltages between 0 and the so-called supply voltage, or VCC. Imagine a very long period with 50% duty cycle. In the on time, you need to charge a capacitor which is able to carry over and supply voltage while the pin is turned off. In long periods, the capacitor has to be charged a lot, hence a large capacitor is required. A shorter PWM period results in a smaller capacity requirement for the capacitor, since the charge and discharge times are much shorter now. This allows physically small-sized external components and therefore reduces total system costs. Setting the timer in phase correct mode is very similar to earlier configurations using the WGM bits in the timer configuration registers. They need to be either 1 or 5. COM&X chooses between a normal or inverted waveform like before. Do not forget to configure the pin to be an output port, otherwise no signal is emitted. Like in the fast PWM mode, the top can be set manually using the OCR. In that case, there will be no PWM available on the OCRnA pin. Okay, that ends the session about the phase correct PWM mode. In the next session, the last mode is introduced, the phase and frequency correct PWM mode. First of all, in the ATmega 328P, only timer 1 offers this kind of functionality. No other timer does. The main difference between phase correct and phase and frequency correct PWM mode is the occasion at which OCR is updated. While this mode is practically the same compared to the phase correct PWM mode, it differs only in a specific scenario, and that is when top is set manually using OCRnA. Let's see when OCR is updated in the various modes. At the beginning of this chapter, we said that OCR is double buffered, which means that the value that a program stores in this register might not be updated immediately, but at specific events. In normal as well as CTC mode, the update is immediately, but this is not true for the PWM modes. While in the phase correct mode, the new value is copied to OCR when TCNT reaches the top value, for the phase and frequency correct PWM mode, it happens at the bottom. So what is the impact of that little change? The yellow circles indicate the time when OCRnB is updated if a new value is written to it. For phase correct PWM, it is at the top. For phase and frequency correct PWM, at the bottom value. The sawtooth-like waveform of TCNT of both modes is the same. The difference might not be visible immediately, but it seems that some of the toggles of OCRnB are cancelled, such as this one, which is missing here. And they are cancelled in case it cannot be guaranteed that the lower part of the OCRnB signal cannot be symmetric around the period. In the upper diagram, this right side here after the top can be different from this part. This is due to the fact that OCRnB has been updated when TCNT reached top. It is not possible to do that in the phase and frequency correct PWM. The waveform is always symmetric around the top value of TCNT1. If that symmetry cannot be established, the toggle is skipped entirely and postponed till the next period. It prevents that spikes or glitches are created even accidentally. And we already said that glitches are bad, especially for motors, a scenario phase correct PWM modes are destined for. To configure the timer to the phase and frequency correct mode, set the WGM bits to 8 or 9 to use ICR1 or ICR1A respectively. While we already encountered OCR, what is ICR1? Even in the TCCRnB, there are different settings now, such as ICNC1 and ICES1. That is new and no other counter has this, so timer 1 is special in more than one way. Let's compare the differences between the counters in the next session. In this session, we briefly summarize the differences between timers. This table shows that all modes are available in all timers, except the phase and frequency correct mode, which is exclusive for timer 1 only. The same is valid for the ICU and ICR, which we will introduce in a minute or two. Since timer 1 has more modes, more WGM bits are required to choose the desired mode. Further, while timer 0 and timer 2 have only a TCNT of 8 bits in size, timer 1 is double of that, so it's able to count up to 65,535 instead of 255. Timer 0 and timer 1 can take signals through pin T0 and T1, while timer 2 can be connected to a crystal to have an independent clock signal that can be different from the system clock. Timer 2 also allows 2 additional prescaler settings compared to the other timers. So, what is the ICU or ICR all about? Having a look at the block diagram of timer 1, we see that apart from 2 compare units, there is an additional unit called input capture unit with a register ICR and an input pin ICPN. What does this unit do? Magnifying the unit reveals that an input signal comes either from an analog comparator or directly from ICPN. We will have the analog comparator in detail in the chapter when we talk about analog to digital signal conversions. So much now. It generates a signal if a voltage crosses a preset threshold. So either ICPN or the comparator are used as an input signal depending on the configuration of the ACIC signal. Then a noise canceller can optionally remove noise based on the IC and C setting. An edge detector will create a signal either at the positive edge or the negative edge of the incoming signal if ICES is set to 1 or 0 respectively. This edge detector is therefore similar to the one of the TN pin that we had earlier. After the processing of the signal is complete, it is forwarded to the ICRN, a 16-bit register. Here is how it works. If the signal is sent, the value of TCNT is immediately copied to the ICR. Therefore, a timestamp of the incoming signal is created. Every time the incoming signal is detected, the value is copied, hence it always overwrites the previous one. Therefore, that ICR needs to be read as soon as possible in your program. What can you do with that information? There are multiple scenarios. One of them, you could determine the period of a regular incoming signal, for instance, by calculating the difference between two consecutive ICR values. One interesting detail shown here is this temp register, which is half of the ICR, and TCNT, which are 16-bit in size. The purpose of that register is to guarantee valid values when reading from or writing to the TCNT or ICR. The ATmega is an 8-bit MCU, so the data bus, which transports the data between the CPU, the ports, and also the timers, etc., is 8-bit wide as well. So transporting 16-bit will occupy the data bus twice. Here's how it works. Imagine the value of the TCNT is 00FE in hexadecimal format currently. In your program, you would like to read the TCNT value. After the clock cycle, the timer is incremented to 00FF, and that is the value that is to be read. So the upper byte is copied to the temp register and the lower byte is put on the data bus. In the next clock cycle, the TCNT is incremented to 0100, while the value in temp is copied to the data bus. The read value is then reconstructed from the two data bus reads, and the intended value of 00FF has been successfully transferred from the TCNT to your program. Imagine that temp does not exist. Again, TCNT is read when its value is 00FF, so the lower byte is copied to the data bus and read by the program. In the next clock cycle, TCNT increments again to 0100, and at the same time, the upper byte is put on the data bus. However, this value is incorrect, and the read value is, instead of 00FF, it is 01FF, a value in the future that the TCNT has not reached yet. The usage of the temp register is entirely transparent, and you do not have to adapt your program to use it. Just read 16 bits directly from TCNT. Everything is done automatically. If the input capture unit is not required, then ICR can be used to store the top value. Earlier, the timers had to give up one compare unit, since OCRnA was used to store the desired top value. In case of timer 1, the developer has a choice if a top that is lower than max is needed, either OCRnA as usual or ICR. In case ICR is chosen, obviously the capture unit is deactivated. If the OCR or the ICR is used for the top value is determined by the WGM bits, and this choice is available for all modes except the normal mode, whose TCNT always runs till max. Interestingly, some other modes are available in timer 1 that cannot be found in the other timer configurations. For instance, some standard max values are available for the fast PWM and for the phase correct PWM, such as a limit to 8, 9 or 10 bit. This chapter just gives a short overview of the timers. I tried to be as close as possible to the reference manual, which is available in the resources folder. We will come back to timers in the next chapter, in which I will show you the workings of the interrupts. In this chapter, we talked about timers. I showed The modes that the timers can run in explained the inner workings of the hardware units and showed how to configure those. We talked about clock sources and prescalers and the difference among the timers that the ATmega 328P possesses. What we skipped entirely are interrupts, which are essential when timers are used. For instance, if the input capture unit copied the value from TCNT to ICR, how will the software ever get to know that such an event occurred? The events might occur in irregular intervals, and checking ICR for a change will consume CPU computation resources. Or another scenario, you use T2 to measure when 1 second has passed using timer 2 as a real-time clock. How will you get to know that the timer overflowed? These are all scenarios where interrupts generated by timers come into play. They reduce resource utilization and programming efforts tremendously. Since they are so important, they are handled immediately in the next chapter. See you in a bit, and thanks for watching.